All right, let's put on our detective hats. Today, we're diving into a crime scene, but it's not what you think. The scene is your data set, and the criminals are these hidden saboteurs, variables that are secretly messing up your entire model. We're going to unmask them. We're talking about multicollinearity.
So let me ask you this. You've built a model, right? The results look pretty good. But what if I told you that underneath it all, some of your variables are so tangled up together, they're making your conclusions totally worthless? It's a scary thought, but it happens all the time.
So here's our investigation plan. We'll start with the first clue, just figuring out how variables move together. Then we'll get our detective toolkit ready to properly examine the crime scene, which is the multicollinearity problem itself. After that, we hunt for the culprits, and finally, we'll close the case.
Okay, first things first. Like any good detective, we have to start with the fundamentals. The very first clue in our investigation is simply understanding how variables relate to each other.
First up is a tool called covariance. It basically just tells you the direction of a relationship. If it's positive, the two variables tend to move in the same direction. Think about giraffes, for example. Taller giraffes usually weigh more. That's positive covariance. But here's the catch. The actual number you get depends on the units you're using, which makes it really hard to compare things. It's not a great tool for our detective kit. And that's exactly why we have our next tool, correlation. You can think of this as the superpowered, much more useful version of covariance. It standardizes everything, boiling the relationship down to one simple number that's always between -1 and +1.
Let's just put them side by side. You can see right away why correlation is our go-to. Covariance, its range is all over the place, and its units are weird. It only gives you a vague direction. Correlation, on the other hand, is clean. It's stuck between -1 and +1, has no units, and tells us both the direction and the strength of the relationship. Way more useful for our investigation.
So what does this actually look like? Well, when the correlation, we often call it rho, is 0, your data points are just a big old random cloud, no pattern at all. But as you crank that number up to, say, 0.7, you start to see a clear upward trend. At a perfect 1.0, it's a straight line. And going the other way, down at -0.9, you get a really tight downward sloping line. The closer you get to 1 or -1, the stronger the signal.
But hang on, just when you think you've got this figured out, there's a huge plot twist. A correlation of 0 does not always mean there's no relationship. And this is a trap that a lot of people fall into.
Now check this out. In this table, y is perfectly, flawlessly determined by x. The formula is just y equals x squared. You can't get a more perfect relationship than that. And yet, their covariance is 0, which means their correlation is also 0. What on earth is going on here?
And here it is. This is the big reveal. Correlation is a specialist. It is only looking for linear relationships, straight lines. It's fantastic at that, but it is completely blind to anything that's not a straight line, like that perfect curve we just saw. And that is a massive limitation you have to remember.
And that very limitation, that blind spot, leads us right to the scene of the crime, the problem of multicollinearity. So what is this big, scary word? Multicollinearity is what happens when your so-called independent variables aren't actually independent at all. Here's that analogy again. Imagine you hire two people to move a big box, but they look and act almost identical. When the box moves, can you really tell who did more of the work? No, of course not. You can't separate their impact. That right there is multicollinearity in a nutshell.
And the consequences are serious. It completely messes with your model. It makes your results unstable and unreliable. It can make important variables look like they don't matter at all. And worst of all, you completely lose the ability to say how much each individual variable is contributing. Your entire analysis is suddenly on shaky ground.
Okay, so we know what the crime is, and we know why it's so bad. Now for the fun part. How do we actually track down these troublemakers? Let's get into the investigation. The first thing we do is put our variables in a lineup. That's what this correlation matrix is. We're just looking at the correlation between every pair of variables. And we're on the lookout for really high numbers. Usually anything over 0.8 is a big red flag. And look here, the Dow is highly correlated with Google and Bank of America. We've got our first suspects.
But that matrix only shows us problems between pairs of variables. What if there's a whole gang of them working together? For that, we need a more advanced forensic tool. It's called the variance inflation factor, or VIF. It tells us how much any one variable is being explained by all the other variables combined. And the rule of thumb is pretty simple. If the VIF score is over 5, you've probably got a problem.
And here we go. The forensic report is in, and will you look at that? The Dow Jones variable has a VIF score of 5.45. That's above our threshold of 5. Bing! This thing is suffering from severe multicollinearity. We found our main culprit.
We found him. The saboteur is in our sights. Now it's time to close this case and fix the problem.
We've got a few ways to handle this. The simplest approach? Just drop one of the highly correlated variables. In our case, the Dow variable with that high VIF score is a prime candidate to get kicked out of the model. For trickier situations, you can use more advanced techniques like principal component analysis, or PCA, which basically combines the overlapping information from multiple variables into one new, clean variable.
So, the next time you build a model, don't just stop at the surface-level results. I want you to be a detective. Dig deeper. Investigate the relationships between your variables, because you just might find a saboteur hiding there in plain sight. Thanks for joining the investigation.